Thanks. I'll wait for it to turn red. Good evening, everyone, and welcome to this evening lecture presented by the Geotechnical Division of SAICE. The topic for this evening is on piled foundations. It's presented by Gavin Byrne from Frankie, and it's a continuation of the lectures we had a few years ago. Theme was back to the basics, to get the basics of our industry just firmed up again. The lecture will start pretty soon with Gavin speaking. Just a few comments on how we'll run it. You will see Gavin will speak, and you will also see the slides from his presentation. We're also recording the event, and it will be available on our website in the near future. We're busy with revamping the website, and we are also in the process of applying for CPD points for the lecture, and we'll also inform you about that. And then you will see on the right-hand side of your screen, there will be a chat column that you can you will see where the comments will be listed. It will open up towards the end of Gavin's presentation, and you can then type any questions that you may have that you want to pose to Gavin. You can type those questions in there, and then at the end of Gavin's talk, our moderator, Brett Markides, he will then select questions from that which you've posted, and he will then read them out loud to Gavin, and Gavin will then be able to answer the questions which you have posted. We will not be able to get through to all the questions. Brett will choose the questions that he will pass on to Gavin. So as we continue, let me just say a bit more about Gavin Byrne. I think many of us in South Africa know him very well. For those who do not know Gavin so well, Gavin obtained his BSc in civil engineering from Wits University in 1971, and then in 72 he joined Over Arab as an engineer in training, and then after 4 years he moved to the structural division for 3 years, and then eventually he got back into the geotechnical division, where he was an associate partner and involved in site investigations and detailed design works. And many of his designs at that time were then done for Frankie Pile. Then in 1987, Gavin joined Frankie Pile and has been involved in major designs of design works for piling, lateral support, ground improvement, and near-shore marine works. Gavin has authored many geotechnical publications, most notably a guide to practical geotechnical engineering in Southern Africa, what we know widely as the Frankie book or the Frankie Blue book. And Gavin has authored 3 editions of this book. The third one in '95, the fourth one in 2008, and the 5th one was published last year at our African Regional Conference. It was brought out in 2019. And Gavin has received the Jennings Award from our division in 1988, and he also won the Geotechnical Gold Medal in 2003. So Gavin is currently the Group Technical Executive of Frankie Africa, which is part of the Keller Group. And I cannot think of a more qualified individual to share with us the basics on piled foundations. Thank you, Gavin. Please carry on.
Thank you for the kind introduction, Jacobus. Much appreciated. Good evening, fellow geo-practitioners, ladies and gentlemen. It's my honor to be requested to present this talk for the Geo Division as part of their Back to the Basic series, as Jacobus mentioned. The series commenced a few years ago, and it is my regret that my talk has been delayed for so long due to the preparation of the 5th edition of the Frankie Blue Book, which was launched, as Jacobus said, last year at the African Regional Conference. I have used the Blue Book as a reference and have structured this talk around answers to 8 basic questions, covering the installation, design, and problems associated with pile foundations as a widely recognized and robust foundation solution. The first basic question is, what are piles and how do they function? They are columnar structural elements in a foundation system. Their function is to transfer the applied superstructure loads through weak and compressible strata or water to underlying competent horizons or bedrock. Timber has been used since Roman times, but has recently been replaced by reinforced concrete and steel due to the enhanced compressive, tensile and bending resistance of these modern materials. The function of piles is illustrated by the diagram on the right. The loads applied at the pile head are transferred into the ground by frictional resistance along the pile shaft or by end-bearing resistance at the pile toe, or a combination of these two elements. Small movements of the pile shaft are required to mobilize the ultimate shaft friction resistance, generally less than 15 millimeters. Significantly larger movements are required to mobilize the ultimate base resistance, approximately 10% of the base diameter, and for a large pile, that movement could be 200 millimeters or more. The combined shaft and base resistance capacities, together with a wide range of available sizes and installation methodologies, allows a single pile to carry an applied working load of between 50 and 50,000 kilonewtons at relatively small movements, typically less than 25 millimeters, which is Tezagi's magic number. The second basic question is, how is a piling solution evaluated and engineered for a particular application? The quote from M.J. Tomlinson's widely recognized book, Pile Foundations and Construction Practice, provides a succinct answer to this question. Tomlinson says, piling is both an art and a science. The art lies in selecting the most suitable type of pile and method of installation for the ground conditions and form of the loading. Science enables the engineer to predict behavior of the piles once they are in the ground and subject to loading. This behavior is influenced profoundly by the methods used to install the piles, and it cannot be predicted solely from the physical properties of the pile and of the undisturbed soil. Tomlinson also recommends a knowledge of the available types of piling and methods of constructing pile foundations is essential for a thorough understanding of the science of their behavior. The third basic question is, what pile types and piling methods are available in Southern Africa and possibly most of Africa? Both ground displacement and replacement pile types are offered by most piling contractors in our region. 5 different driven and 8 board piling methodologies listed below can be considered for most Southern African projects and geotechnical conditions. For driven piles, the Frankie pile has been widely adopted in a broad range of ground conditions and project applications. The recently introduced Ductile Pile is a proprietary driven micropyle solution for light and medium loaded structures. The remaining driven piling methods are used for specific ground conditions or applications. Of the 8 board pile methodologies, the auger, either open drilled or cased, is the oldest and most widely used bore pile suitable for a wide range of ground conditions and loading requirements. The continuous flight auger pile is also widely used in a range of ground conditions and is easily installed and is economical. The bore pile solutions, auger understory, oscillator and rotor pile, are limited to projects with specific requirements and difficult ground conditions. The Micropyle has recently replaced the four-room board pile where limited operating space and limits in terms of establishment costs are present. I'm going to briefly outline the installation methodology and salient uses and characteristics of each pile type listed. The detailed installation methodologies are well documented in the Blue Book for each of the pile types presented, and would require further reading to really become fully aware of them. The Frankie is a bottom-driven pile which is driven to the required depth, and an enlarged base is formed by the expelling a dry mixed concrete below the pile toe. The pile is reinforced and concreted, and the pile tube is extracted. The pile exhibits excellent load versus settlement characteristic and has medium load capacity with 4 pile diameters up to 610 millimeters available. The photograph on the left shows the Frankies being installed on a large project at SAICE in Natal, where one of the deepest Frankie piles ever installed in our region, 22 meters, has just been completed. The tube pile is installed by either bottom or top driving segmental lengths of tubes ranging from 450 millimeters to 3 meters in diameter. The bottom driven methodology is similar to the Frankie, but the tube is permanent. The top driven alternative can be executed with an open or closed tube, and the pile can be vibrated or driven with a variety of hammer types. The pile is ideally suited to marine conditions and can be reinforced and concreted in situ to enhance its structural capacity and durability. The ductile pile is a proprietary driven micropyle installed with a hydraulic hammer fitted to an excavator. A range of high quality prefabricated cast iron steel tubes with specially designed couplings are top driven and grouted continuously during driving, as shown in the installation diagram. The grouting is achieved through the grout shoe and fills the annular void created between the oversized shoe and the pile shaft, permanent pile shaft. The pile has been recently introduced and is used for light and medium loaded structures. The driven precast pile is ideally suited for poor ground conditions with deep founding horizon, which are common in the estuarine locations on the east coast of the southern African continent. The pile shaft is prefabricated in workable lengths and incorporates special couplings to join each pile segment during the top driving process. The piles have a medium load capacity and can be driven to practically unlimited depth. The installation requires careful handling procedures to avoid damage to the concrete pile shafts during installation. The photograph illustrates a 300 millimeter square precast concrete pile in Port Louis, Mauritius, installed to depths of approximately 30 meters in estuarine deposits, which are encountered in the Port Louis area of the island. The driven steel H-pile is installed in a similar manner to the precast concrete pile, but the pile has excellent penetrability and is not susceptible to damage during driving. The universal column and bearing pile sections available provide the pile with a medium load bearing capability, and the pile is suited to driving through obstructions typically found in waste and disposal sites. The auger pile is the oldest and most widely used board pile in the region, and a wide range of pile diameters from 450 millimeters to 2 meters in diameter can be installed. The modern drilling piling rigs are hydraulically powered and are capable of delivering high torque and crowd, which facilitates the drilling of large diameter piles to great depth and into competent bedrock. A wide range of drilling flights and buckets shown on the illustration are available to optimize drilling penetration and extraction rates. The piles are open drilled holes where there is no risk of hole collapse. The base of the hole is either cleaned mechanically or manually, depending on safety regulations. A full or partial length reinforcement cage is lowered into the empty hole, and the pile is concreted with a high slump concrete to the required level. The presence of boulders as well as a shallow or perched water table generally preclude the use of this pile type. The auger piles can carry a wide range of loads from light to very heavy. If cleaning of the pile base cannot be guaranteed, care should be exercised in estimating the pile base capacity. The temporary cased auger pile has become a common pile type where hole instability is likely when an auger pile solution is envisaged. The casing eliminates the risk of hole collapse and limits water ingress. Casings of between 6 and 800 millimeter diameter are installed in generally 6 meter lengths to the required depth to ensure hole stability. Casings can be drilled in, generally single wall, or oscillated, generally double wall. Oscillating is required for very hard or difficult penetration conditions. The pile is concreted directly or with the tremie, and the casing is removed after concreting. The auger and the slurry pile, or barrette, as it sometimes is constructed, are generally utilized where high load capacity is required in deep founding conditions with a shallow water table. The piles are installed using a similar process and drilling tools to the auger pile, but hole stability is maintained by a thixotropic bentonite fluid in the pile bore. The level of the bentonite fluid in the hole must provide a positive head of between 1.5 and 2 meters above the water table at all times. The piles are often socketed into bedrock to provide the high load capacity generally required. On completion of drilling, the hole is cleaned by suctioning, and the bentonite slurry is cleaned to ensure no contamination or inclusions in the concreting process will occur. The pile shaft reinforcement cage is lowered into the hole, and the pile shaft is concreted using a tremie in a continuous operation. The photograph on the slide illustrates a typical bentonite handling plant used for this pile type. The next board pile type covered in this talk is the continuous flight auger pile, which is installed with a continuous hollow stem auger using similar drilling to the auger pile, drilling techniques and machinery to the auger pile, but adapted to accommodate the CFA procedure. The auger is usually drilled to a predetermined depth or refusal on completion of On completion of the drilling, concrete or grout is pumped through the hollow stem, and the auger flight is lifted at a controlled rate to ensure the void below the pile tip is fully concreted at all times. The pile is concreted to the surface and the reinforcement cage lowered or vibrated into the fluid concrete after completion of the process. The piles are generally partially reinforced unless full-length reinforcement is required from a design perspective. Piles up to 900 millimeters diameter can be installed, providing medium load capacity, which can be installed in a wide range of soil conditions in a shallow phreatic surface condition. To ensure pile shaft integrity and satisfactory pile performance for the CFA pile, the process requires skilled operators to control and record this installation process. A derivative of the CFA pile is the full displacement screw pile, with modification of the auger flight to effect soil displacement instead of the CFA's soil replacement. The operation of the flight is shown. The operation of the displacement flight is shown on the diagram and exhibits the lower portion of the flight affecting soil loosening, where densification is affected by the central portion of the body, the flight body, and stabilization of the displaced soil in the upper portion of the flight. The installation and construction of the pile shaft concrete is similar to the CFA pile. The pile type is more suited to weaker soil profiles since the soil replacement technique requires the equipment to deliver high torque to ensure sufficient pile penetration can be achieved. The pile can be rapidly installed in suitable soil profiles, but is subject to the same limitations as the CFA pile. The forum board pile, widely used in limited access conditions or where low equipment establishment costs are a primary consideration. The pile type is being phased out due to its labor intensiveness and slow production. A single pile diameter is installed by of 410 millimeters, is installed by driving segmental screw-coupled casings with continuous soil removal during advancement of the casing, shown in the installation sequence. A bulbous base is formed at the pile toe, and the pile shaft is manufactured with a similar process to the Frankie pile, but is being replaced with the Micropyle now. A specialist pile for very difficult soil conditions is the oscillator pile, and is highly suitable for those conditions. The pile has a high load capacity, it provides a high load capacity, and is mostly used where penetration of large boulders and significant depths of hard rock is required, which make the pile suitable for large river bridge foundations or karst dolomitic conditions. The installation process is similar to the smaller forum board pile, with large casings up to 1.8 meter diameter installed using a high capacity oscillator shown in the two photographs. The large casings are usually robust double wall steel tubes fitted with specially designed couplers. Soil removal is carried out with grabs or auger flights, and rock penetration is effected by heavy chiseling or drilling with core barrels. Large and deep founding depths can be achieved, and the pile is often permanently lined with a thin wall steel liner. The pile shaft is reinforced and concreted in a continuous operation with progressive removal of the heavy duty temporary casing. The pile type is, however, both costly and the installation process relatively slow. The rotor pile is installed with the down the hole hammer technique, ideally suited to rapid penetration of hard rock horizons. The pile is suited to similar applications to the oscillator pile, but due to the maximum diameter of 600 millimeters generally available, medium load capacities can be achieved. Significant volumes of compressed air are required to operate the hammer and expel the spoil from the drill head up to the annulus between the casing or the pile bore and the drill string. The pile can be installed without casings, but proprietary casing methodologies are generally used for pile applications. The casing can be either permanent or temporary, and the pile shaft is reinforced and concreted or grouted for smaller diameters, as shown in the installation diagram. The pile is commonly used for river bridge foundations with moderate scour depths and where boulders are present. And rock penetration is required as depicted in this photograph of piles for a small bridge in the northern province of Southern Africa. The micropyle is defined as a bored pile with a diameter always less than 300 millimeters and has recently replaced the forum bored pile in Southern Africa as mentioned previously. The micropyle is ideally suited to underpinning applications and can be installed in a wide range of conditions with limited access and headroom to support light loads or structures with a high uplift load requirement. The micropyle can be installed with a variety of methods and can be reinforced using casings, heavy reinforcement, or high capacity threaded hollow bar. Grouting is always used for the micropyle and has a major impact on the pile capacity, and neat cement water grouts are generally used. Post-grouting techniques can also be adopted to increase the load transfer capacity to the surrounding soil or rock mass. The fourth major question is, what information is required to choose and design a pile foundation? The answer to this question is simply as much as possible. For each of the four main areas of information affecting the successful implementation of a piling project. Detailed structural information, but particularly the imposed loads as well as settlement and durability requirements are fundamental. Geotechnical information is the most important for both choice and detailed design of a pile, and a well-developed ground profile representative of the full site must be available and must also be supplemented with information on the stability of the bored hole, the level of the phreatic surface, and the presence of obstructions which could affect the choice of both pile type and installation methodology. Environmental information and constraints, as well as operation and financial requirements, are key to the correct choice of pile, which in turn affects the detailed design of the foundation system. As noted in the previous slide, the information obtained from a site investigation is vital to the delivery of a successful project. And the old saying, you will pay for a site investigation whether or not you do one, is graphically illustrated by the right-hand figure comparing site investigation costs to increase in foundation construction costs. And in fact, I have seen a few projects where the 100% is in fact more than 400%. The Site Investigation Code of Practice was published in 2010 by the Geotechnical Division, and the Code of Practice answers the four main questions relating to type and importance of the development, the number of investigation points required in the site investigation, the depth of the investigation required, and the parameters and tests that should form part of the investigation. In situ testing is particularly useful in the empirical method associated with the estimation of pile behavior. And this code is absolutely essential to be adopted by all practitioners, geotechnical practitioners, and all clients and structural engineers should be made fully aware of this code of practice. The fifth basic question is, what piling codes of practice and design methodologies are applicable to our region? The current state of piling codes of practice in South Africa for both design and execution is not satisfactory, and no design code is in existence, and now the only execution code of practice, SWS 1200F, is significantly outdated. The Euronorm Execution Code of Practice for micropiles has been adopted by SABS and is the only modern execution code available. The Coulter Code of Practice for roads and bridges has sections on pile design and execution included, but the code is currently revised and is not a national code. The Geotechnical Division is currently preparing a wide range of geotechnical codes of practice based on limit state principles outlined in Eurocode 7. The piling portion of Eurocode 7 is being considered with the incorporation of a national annex for the design of pile foundations, and the Euronorm execution codes for both board and driven piles are being considered to complement the current Micropyle code of practice. A phased approach should normally be carried out for the design of pile foundations. A conceptual design is often carried out initially. At this stage, the first important and vitally important step is pile type choice, which is followed by an assessment of founding depth, which in turn is followed by a preliminary estimate of pile capacity and settlement using simple working load design methodologies. Following on the likely code implementation using the limit state design approach, the detailed design should incorporate detailed assessment of both ultimate and serviceability limit states for pile foundations. As shown in the figure and on the right of the slide, 4 methods of calculating pile capacity can be used for our region. For driven piles, the driving resistance is used to evaluate the characteristic pile capacity, and static calculations for board piles using empirical correlations based on in situ or laboratory tests are recommended. Eurocode permits the use of pile load testing for both the pile capacity and settlement performance evaluation. The pile shaft portion, the pile shaft friction coefficient portion of load capacity is given for both cohesive and cohesionless soils and has been developed by many researchers, some of which are shown graphically on the 2 slides, one by Berezentsev and the other by Skempton. Several researchers have developed both shaft friction and end bearing coefficients for piles in I'm sorry, I'm on the wrong slide. Let's go to the next slide. Sorry. Several researchers have developed both shaft friction and end bearing coefficients for piles in rock. These coefficients, used in conjunction with the unconfined compressive strength, often incorporate corrections to take rock structure into account in the evaluation. For preliminary design, the direct correlation with in situ tests shown on the slide can be used for shaft capacity, and similar correlations used for end bearing resistance for both piles in cohesive and cohesionless soils. The uplift and lateral load capacity is often a secondary requirement in pile design, and simple calculation methodologies is permissible. For uplift loading, the uplift resistance can be based on using 70% of the compressive resistance of the pile, or the Meyerhoff and Adams method for base enlargement piles, illustrating on the slide on the left. The lateral resistance of piles is a complex issue requiring numerical methods of analysis. The simple method of analysis using a point of virtual fixity can be used for preliminary design, or where lateral load is a minor loading condition. Limit state requirements of Eurocode require both single and pile group settlement performance to be evaluated. Due to the empirical nature of the assessment of pile behavior, the load transfer function method for single piles is an effective method for reasonably accurately determining performance. And the method developed by Fleming is illustrated on the slide showing the pile shaft settlement performance over the full range of loading. Pile group settlement is a complex issue, and simplified methods can be used. The equivalent raft method proposed by Tomlinson and illustrated on the slide is often used and provides relatively accurate assessments. The modern availability of numerical methods, however, provides a more satisfactory approach and should be used if accurate settlement assessment is required. The structural design of pile shafts should be based on piles acting as short-braced axially loaded columns in accordance with SABS 10100. For preliminary design, the piles can be sized using the working load pile stresses being limited to 25% of the concrete grade chosen for the piling project. Unsupported fixity conditions, if they exist, should be taken into account, and construction tolerances and eccentricities must also be evaluated in determining pile shaft bending moments and required reinforcement. The sixth basic question is, what is required to ensure a pile is robustly designed and installed satisfactorily? The answer to ensure this requirement is that adequate and relevant geotechnical data is obtained once again. Appropriate design parameters should be utilized. Proven empirical correlations are normally applied. The correct choice of pile type is fundamental, and that must be made at an early stage of the project. Sound and proven design methodologies should be used and codes of practice adhered to. Pile construction should follow applicable norms or accepted and proven practices. Detailed construction and quality assurance procedures should always be available before the commencement of a project, and the documentation should be verified by supervising authorities. Both load capacity and pile shaft integrity should be tested for site conditions on most projects and is a vital part of furthering the knowledge of pile foundations in conditions in a particular region. To ensure both the design and execution of the piles has been carried out appropriately on a particular project, it is advisable that pile load testing is carried out, even though it often presents both economic and program challenges. It is advisable that pile testing is allowed at an early stage of the project development, and it should be carried out using trial piles, particularly on large projects. Both static and dynamic testing methods can be considered, with the static load test providing direct measurements, while dynamic methods require correlation with static load test results. The two types of static tests are illustrated on the slide. The Osterberg cell can be set up to evaluate the shaft friction and end-bearing components separately, and is ideal to use before any contract pile installation procedure is commenced. The pile shaft design can be reinforced at an early stage, and the installation procedures adjusted to incorporate this optimization. The test is, however, proprietary and is carried out by and is costly, but the information obtained can be effective, particularly on large projects. The most economical and widely used pile testing method carried out is illustrated on the left-hand portion of the slide, where the direct load test involves the application of axial load with a reaction beam anchorage or kentlage. Two types of dynamic testing are available worldwide. The statnamic test is not widely used and to date has not been used in our region. Dynamic testing using sufficient hammer impact energy to the head of the instrumented pile, as shown in the diagram, has had limited application in our region, but has been used for driven piles on marine projects where it is difficult to access static load test methodologies. Pile shaft integrity should be carried out on a reasonable percentage of piles installed on virtually every project. Where large diameter board piles carrying heavy loads are used, the ultrasonic test should be incorporated into the testing schedule. The test is effective in locating zones of transmission anomalies, but the results require expert interpretation and tactile verification of possible defective concrete. The impact frequency test shown on the right of the slide is both cost-effective and quick to verify potential anomalies in pile shafts, and should be used on most projects with both driven and bored piles. Like the ultrasonic test, the method requires expert interpretation, and tactile verification is required to detect actual defects. The seventh basic question is, what problems can be encountered with pile foundations in our region? The first and probably most commonly encountered problem is strength and integrity defects of concrete in cast in situ pile shafts. The second most common is inadequate geotechnical investigation, which has been stressed in by various authors and previously in this presentation. Crucial. The incorrect choice of pile type is also a fairly prevalent problem, particularly for auger piles where they are chosen in unstable ground conditions or where there is a shallow phreatic surface. Problem soils have also indicated, or problems are also encountered on problem soils, particularly the dolomitic cast conditions, also heaving subsoils and collapsing sands. The use of inappropriate installation methodologies and inadequate equipment is often used, particularly in remote portions of the country, of the regions in Southern Africa. Environmental issues are also common, particularly in urban areas, and vibration and noise needs to be carefully considered for each project. The least common problem encountered is flawed pile design, and failures due to this are not particularly common, particularly in Southern Africa. I'm briefly going to present a few case histories highlighting most of the problems encountered in the previous slide. These are going to be brief, as I say, and are based on my experience on these particular projects. The first the first case history is incorrect choice of pile type on a Tanzania power plant, which was a Frankie project, which was tendered for on driven precast concrete piles, with a Frankie pile alternative proposal offered and rejected by the consultant, who provided the installation procedures based on a minimum number of blows, as is commonly used in the Netherlands. The soil profile was particularly difficult, and reasonably shallow, dense sands were present. The installation procedure of minimum number of blows resulted in the piles being completely damaged before the required blow count was achieved. The penetrations were not what was anticipated by the design engineer, who was based in the Netherlands, and major cost increases and delays were encountered to adjust the pile and remanufacture a significant number of the pile shafts which were damaged. Problem soil conditions encountered. I'll give you three instances where problem soil conditions caused significant increases in piling costs and significant delays to programs. The first are dolomitic conditions. Piles installed in the cast hard dolomitic conditions are almost always problematic, and I don't think there's a piling contractor in South Africa who hasn't made losses on a dolomite piling contract. There are numerous problems of piling problems encountered, and it is almost inevitable. And I believe a webinar on foundation solutions in dolomitic conditions is a good topic that needs revisiting. I think it was visited several years ago, and things have moved on and equipment has moved on since those days. The second problem soil condition, heaving clays, was clearly demonstrated on the piles installed for the Letabo power station. The heaving soils on the Letabo power station site were deeply desiccated by a blue gum plantation, which was removed for the construction of the plant, and significantly larger heave movements of the order of 800 millimeters necessitated the revision to the pile design soon after the contract commencement. A deep horizon, my apologies. The pile shaft isolation was significantly increased from, I think, initially 12 meters to in excess of 25 meters on the project, and the voids left below the pile caps were generally of the order of 200 millimeters. And finally, after about 5 years, the pile caps on the main turbine hall were being heaved off the underlying large diameter supporting piles, and a mining project had to be undertaken to provide a void on the pile cap some 5 years after the completion of the project. Collapsing sand problem conditions, were encountered on the Moselle smelter. A deep horizon of highly collapsing residual sandstone became evident soon after the commencement of the contract, with relatively shallow pile founding depths anticipated. After a series of tests on the saturated properties of the collapsing soils using trial piles, the founding depths were more than doubled on the project. I have a few slides following this slide which will illustrate some of the properties of the collapsed soil in a saturated condition. The inappropriate installation or inadequate equipment problem encountered was clearly demonstrated on a marine harbour terminal in Walvis Bay, where approximately 1,000 1.3 metre diameter auger underslurry piles with a founding depth of 35 metres were installed from a reclaimed island. The piles were installed to support a fairly large reinforced concrete berthing deck. After dredging on completion of portions of the deck structure, the installed piles exhibited major defects on more than 90% of the piles installed. The defects were due to poor bentonite management process, slow and antiquated piling equipment with construction time of more than 5 days per pile. The whole key piling solution required replacement of all of the piles on the key structure and delayed the project by more than a year and a half. Vibration is often a problem with driven piles, encountered with driven piles, particularly in urban areas, and the problem is mostly perception rather than actual. Vibration effects were studied by my colleagues Nicole Chang and Brett Markides, and the paper they published provides valuable guidelines on the effects of vibration. And I will show you in the following slide some of their research information. This slide shows the 2 phases of the Moselle project with 8 pot lines approximately 2 kilometers long from end to end, and a huge number of piles were installed on the project. The project is near the city of Maputo. The typical geological cross-section on that site, indicated by the cross-section, by the graphic, shows the purple color shows the deep collapsing residual soil profile almost entirely across the site to depths of up to 16 meters. The typical profile in the dry condition is shown by this Dutch cone penetration test, indicates tip resistance values in excess of 20 MPa in the dry condition from a depth of about 3 meters. And it's clearly seen why the initial piling depth of 6 meters was chosen for the project. After a trial saturation area, Dutch cone penetration tests were carried out, and you can see that the point resistance values had significantly decreased to well below 5 megapascal and were generally 2 MPa on average. This resulted in marked difference of pile performance, particularly the base after saturation. The green line, you can see the load to twice working load, the performance to twice working load, showing settlements less than 10 millimeters, and after saturation, using the same pile, the pile failed at a load of approximately 1800 kilonewton, which was the working load capacity of the pile. This is just a quick illustration of the vibration, the requirements presented by Dr. Chang and Brett Markides in his publication, which is definitely worth looking at, showing clearly that vibration effects are very limited to close to the driving position for a wide variety of structures. They also give they also give recommendation in terms of distance for construction to the various ranges of buildings or structures, ranging from 4 to 30 meters, where visible damaged buildings are obviously susceptible to vibration damage. The final question, where to for the piling industry? There have been marked advances in piling methods and equipment capability and production in the last decades, and this will continue, but will likely be on a reducing scale going forward. The development of sophisticated monitoring and instrumentation technologies will increase and refine our understanding of pile behavior. Increased automation and data acquisition of the construction process will provide significant enhancement in the quality of piles installed. Environmental, sustainability and economic considerations will present a major challenge to piling, as well as a well-established and robust foundation solution. Ground improvement. The question is it a more environmentally sustainable and economic alternative to piling? The answer to that question is probably yes, and it requires careful analysis before any foundation solution is evaluated for a particular site. And the full range of soil improvement solutions, but more particularly soil compaction and some soil replacement solutions, are often more economical, sustainable and environmentally friendly than the piled foundation solution, particularly large piles to great depth where large volumes of concrete are required. Thank you for your attention, and I will now be answering, hopefully, your questions put to me. Thank you very much.
Thank you for that, Gavin. Hi all, my name is Brett Markides. I am moderating tonight's evening lecture. A short while ago, I opened up the Q&A, so please, if there are any questions, please post your question. I will then repeat the question to Gavin out loud, and Gavin will try answer. It is about 6:10 at the moment. We have allowed for about 15 minutes of questions, so unfortunately we won't get to everyone's question, but we will try answer as much as we can. Okay, Gavin, I'm going to look for some questions here. The first question here: thank you for an interesting talk. Will the presentation be made available electronically to attendees? Sorry, Gavin, I can answer this.
Thank you.
The presentation is being recorded, and we will publish it on the GeoDiv website, so you can get it there. All right, Gavin, another question. What is the best pile type for liquefaction conditions?
That's a very good question. Clearly, the most relevant loading condition is lateral loading, and the pile type must certainly, in severe liquefaction conditions, must be able to penetrate greater than 15 meters, because liquefaction is generally encountered in the upper 20 meters of a soil profile. Usually, liquefaction is a loose, silty sand phenomenon, vibration and liquefaction of a loose, silty sand. So both driven and board piling solutions can be employed. The most robust is probably a driven tube pile, which is capable of sustaining both high horizontal loads and can be driven to great depth.
Thanks, Gavin. Another question. I am interested to hear what Gavin has in mind when he mentions that better techniques for founding in or on dolomite have become available recently.
Yeah, as I was saying in my talk, dolomitic conditions are extremely difficult for pile installation, and because of that difficulty and the uncertainties of the condition, redundancy, the lack of redundancy of a pile foundation can become one of the major obstacles, together with the depth of installation required, particularly for large large sinkhole development possibilities. A lot of ground improvement techniques have now been or have recently been used and are significantly more effective, more cost effective, and useful in particularly closing the entrance channel to large cavities. So yes, dynamic compaction is one of those, and I believe many of the soil replacement technologies which have a large amount of redundancy might also be applied. But I firmly believe a workshop would be of benefit in this regard.
All right. In your opinion, how far are we from implementing a national or modified international code of practice for piling in South Africa? How can Geotech division members contribute to this goal?
Well, the problem sits with me. I should be chairing the committee that's actually preparing it. But with the book and with COVID and so on, that's been a bit in abeyance, but we certainly in the next 6 months will have a concerted effort in forwarding or advancing this, and hopefully early next year get into a position where we can have the code available, and particularly both the design and execution codes, as they really are vital for piling in the region.
Okay, Gavin, what is your opinion with regards to the inclusion of end bearing capacity in the design of CFA piles installed to rock?
Also a very good question. Unfortunately, some conservative approach should be taken with this in this regard. The piles are obviously the socket conditions cannot be verified visually or tactilely. The installation process is very operator dependent, so it is an extremely wise practice to use conservative end bearing values even in rock conditions. I would not go greater than 8 MPa as an ultimate end bearing resistance.
Okay. Do you recommend a larger end bearing safety factor for CFA piles versus auger piles?
In terms of Eurocode, there's no difference in the factor of safety used for end bearing or shaft friction. In the old working load design methodologies, different safety factors were used for shaft and end bearing. I think generally 1.5 or 2 were used for shaft and a factor of safety of 3 for end bearing. But with the limit state code, this approach is not recommended, but can be used for preliminary design using a working load methodology.
Is it safe to design for end bearing of piles, given that cleaning of the board pile holes are not always satisfactory?
A very good question, which I don't think there's been an absolutely definitive answer, but certainly for small diameter piles, no end bearing should be taken into account. and the rock contribution, the rock section of the soil profile contribution to the pile capacity should be based on socket friction only. Obviously, for larger diameter piles, where it is possible to verify the cleaning condition of the pile base, then certainly higher bearing capacity values can be taken into account. But for under slurry piles or piles where cleaning is not tactilely possible, and control of the suctioning process is debatable, then also end bearing should be limited.
Would you generally use more smaller capacity piles or less higher capacity piles for a foundation solution?
I guess either of those two are applicable, but will depend largely on what pile type is chosen. If a large diameter pile is clearly the most economical and most robust solution, then a single pile will be both technically and economically optimal. But sometimes a large number of piles in a group will provide redundancy and may provide economies, but generally, unless the smaller piles can be founded at significantly shallow depth, I don't believe that as a general principle is applicable.
The design of piles in clays normally uses undrained cohesion values in the estimation of side shear resistance. How does the long-term drain parameter affect the design?
As noted in the talk, particularly the pile shaft values are empirical, and they're based on behavior of piles using the measured in situ test values or laboratory undrained shear strength values. So they are empirical values based on the undrained conditions, and are therefore relevant. Drainage will not affect that portion of the shaft where disturbance of the clay is affected during the pile installation.
Which pile type is generally the most robust pile type?
Yeah, that's that's a fairly open question. It depends how one defines robust, but clearly it depends on the installation methodology. The Frankie of the smaller diameter piles and medium load capacity piles, the Frankie is a very robust pile because of the enlarged base and the control that one can execute on the base. All pile types are effectively robust if properly designed and constructed. And of the board piles, probably the oscillator or permanently cased pile is the most robust due to its durability, its good durability qualities, as well as its large diameter and usually good quality concrete that's put into the pile shaft.
Can the typical shaft stress limit of 8 to 10 MPa be exceeded, and to what?
Well, the limit on there actually is no current limit on the shaft stress that's used. The 10 MPa is generally based on using a 40 MPa concrete 10 MPa working stress is used based on a 40 MPa concrete, and what I said earlier in my talk, the 25% of the 40 MPa gives you 10 MPa. With modern concrete technology, particularly like in the Middle East, significantly higher concrete strengths are used for pile shafts, I think up to 60 or 70 MPa, and therefore working stresses can be increased in accordance with that increased characteristic strength or concrete grade that's used in the manufacture of pile shafts. I wouldn't recommend in our country with the aggregates we have and the quality controls that I wouldn't recommend that more than 40 MPa concrete is used.
Is there a pile type that can possibly be used to improve the strength of slopes?
Yeah, piling is commonly used for slope stability, where large diameter piles are placed as dowels at the toe of the slope. They provide additional shear resistance over that portion of the slope, which will increase the factor of safety. Up the slope, it's very difficult to put in piles because of the slope, but clearly smaller diameter piles or soil inclusions can provide additional factors of safety and improve the slope stability.
What is a reasonable percentage of piles to be integrity tested?
Also a good question. It depends what type of integrity test. Obviously the ultrasonic logging test is a fairly expensive and difficult test, and is only suited really to large diameter board piles. And where piles are carrying high loads and it's vital that the pile shaft concrete is intact, then probably at least 25% of piles should be tested. For where the impact frequency test, which is fairly economical and quick and easy to use, is employed, particularly for small diameter and driven piles, then a large number of piles can be tested and should be tested to check for durability and potential defects. And I would say the 20% could easily be increased to 100%. But it does have program implications, because the test has to be carried out on trimmed piles and can have major problems with main contractors and pile cap construction.
How do SDAs perform under bending moments? I assume this would apply to micropiles as well.
Sorry, what?
SDA, self-drilling anchors, or micropiles.
Micropiles. How do they? Sorry, just repeat the question.
How do micropiles perform under bending moments?
Obviously, micropiles are small diameter and therefore can't take particularly large bending moments. But if thick-walled tubing is used as part of the load, the loading contribution of the micropile, then the thick-walled tube can take significant bending moments. A 300 millimeter thick, 12 millimeter thick, or 20 millimeter thick tube will take a significant bending moment. And obviously, the design can be structurally carried out for this particular situation.
Okay, in terms of codes of practices, are we not complicating design procedures?
That's also a very interesting question. Look, I come from the working load working load methodology. I'm not particularly afraid with the limit state methodology, but I'm becoming so particularly quickly. I believe the limit state is a much more reliable and robust method of design. It's been adopted throughout Europe and in many parts of the world, and it does require significantly more pile design. It's a much more difficult and time-consuming pile design process. But if the conceptual design using working load solutions and simple methodologies provides a robust solution which is only taken to final design stage to complete the quality control and ensure that all the requirements are met, then particularly with computer programming and spreadsheets and so on, I believe the process can become fairly rapid, and once people get used to it, it's a normal process. And I don't think there's any reason why it shouldn't be adopted.
Okay, Gavin, thanks for that. I think just looking at the time, I think we've reached the cap for the questions that we want to pose to you for this evening. So I think we're going to call it there. Unfortunately, like I said, we can't get to everyone's questions, but I hope that we've at least asked some interesting questions and Gavin has answered them to your satisfaction. From my side, Gavin, thank you very much for your presentation. It's been a long time. We've been waiting for you to present, so very happy that finally it happens. And it was thoroughly enjoyable, so thank you very much for that.
Thank you, Brett. Sorry, yeah, carry on.
Yeah, no, carry on.
Yeah, it's been my pleasure, and I must say a steep learning curve for me. I'm a bit BC, but thankfully with my son next to me, I've managed the process to some degree of competence. But also relating to the questions which I couldn't answer, I'm very happy to if the questions are sent to me, and I will reply to whoever sent them electronically or by email or whatever. Okay,
so I mean, with MS Teams, I'm able to download the questions that haven't been answered, and I can share that with you at a later stage. We can see who asked the questions and who we need to respond to. Otherwise, we just share one large email with all the questions and answers. But that's a discussion later.
Okay, no problem. Right. Thank you.
But otherwise, from my side, Gavin, thank you very much. For everyone who joined in tonight, thank you for your time. Thank you everyone who RSVP'd, and obviously thank you to everyone who joined in. The next lecture will probably be our online format again, and we're looking at doing that probably middle of July. So please just look out for the email. The next lecture will be by Dr. Nico Vermeulen, and it should be on site investigation, which should be interesting. Otherwise, again, thank you, everyone. And I think we're going to call it a night. So keep well, stay safe, and thank you very much again. Cheers.